So the next topic is particle motion in polar coordinates. Here we are going to see the polar coordinate versions of velocity and acceleration. The adjacent figure, which means this figure, shows the polar coordinates r and theta of the point P and the polar unit vectors r hat and theta hat at P. So in the plane you have your polar coordinate system, which consists of this point O as the pole and this initial line. Now what do we mean when we say that these are the polar coordinates of P? You join P and O using a line segment, a straight line segment. The length of that line segment is the polar coordinate r, and the angle that this OP makes with the initial line is your theta. And what about these polar unit vectors? The unit vector r hat points away from O so that it's along OP, and its unit vector means its magnitude is 1, and the unit vector theta hat is perpendicular to this. You also see our familiar unit vectors I hat and j hat. I hat is along the positive x-axis and j hat is along the positive y-axis. Now the directions in which these polar unit vectors point, they have names. The directions of r hat and theta hat are respectively called the radial direction and transverse direction at P. As P moves around, as this point moves around in the plane, the polar unit vectors don't remain constant, obviously, because for example say P at some instant P is here, then r hat points in this direction, theta in this direction. But if P comes here, then r hat points in this direction, theta in this direction. But interestingly, although these vectors are not constant, but their magnitudes are constant, that's just 1 because they are unit vectors. That thing does not change, but their directions change, and that depends only on theta, not on r. To see how, you just imagine that your theta is fixed and you change r, which just means sliding the point P on this line, right? If you bring P closer to O, then your r will be smaller. Alright, but that does not really change the direction of this r hat. R hat continues to point in that same direction, and because its magnitude anyway is 1, so it stays constant. So changing r does not change r hat. Similarly, changing r does not also change theta hat. That also continues to be a unit vector which is perpendicular to this one. However, if you change theta, then things change. So you get this interesting fact that these vectors are functions of the scalar variable theta. They don't have anything to do with r. Okay, so r hat, for example, is a function of theta, but which function? This function. R hat is cos theta I hat plus sin theta j hat. So here we have expressed r hat as a function of theta, and also in that we have these fixed unit vectors I hat and j hat. But how? Where is this coming from? This is how. You know that because r and theta are the polar coordinates, so the Cartesian coordinates of P will be these: r cos theta, r sin theta. You already know these things from coordinate geometry. But when you have the Cartesian coordinates of P, then you can express the position vector of P relative to O, which is this vector OP, which we are giving it a name, okay? Vector R is r cos theta I hat plus r sin theta j hat. It's a simple thing. So then what is r hat in terms of this position vector? This position vector has the same direction that r hat has, or we can say it this way also, same thing, that r hat has the same direction as r vector, and r hat is unit vector. So you get r hat from r by dividing by its magnitude. If you calculate the magnitude, you find easily that this is just r. So that means you divide this by r, so that's how you get your r hat. And now we are going to next see what function theta hat is as a function of theta. You have to understand one thing very clearly, that these are just some names, okay. In these notations, this theta alone is not that theta. It's just some vector which depends on theta. Similarly, this is just some vector which is in this direction, and that anyway does not depend on r. To find the unit vector theta hat, what you do, you may get confused at first, but it's not really that difficult. You just slide this representation of theta hat parallel to itself so that its initial point now coincides with the pole. That means you have brought it down and this is its new location. The vector does not change, we do this all the time. Still the magnitude is 1 and direction is same as that one. And now you think of a similar process to find theta hat. You imagine another point like P here along this line, whose distance from O is also r. Okay. Then for that new point, what will be the Cartesian coordinates? R times cosine of pi divided by 2 plus theta. Why? Because for that new point, that distance is r, and what is the angle? The angle is theta plus 90 degrees, because this is 90 degrees, that's why. And that's why I slid it down here to understand that. And what is the y coordinate? The y coordinate will be r times sine of pi over 2 plus theta. So you go through a similar process, and this is how you get your theta hat. But then cos pi over 2 plus theta is minus sine theta, and sine of pi over 2 plus theta is cos theta. So we have got these two vectors, r hat and theta hat, in terms of I and j and theta, because basically they are functions of the scalar variable theta. Now next what we are going to do is we will find derivatives of these vectors with respect to theta. Why do we do so? That's because we are going to need those derivatives to find out velocity and acceleration of p if p is a particle moving in the plane. P is not moving in space in general, okay. P is moving in this plane in any manner depending on the situation, but still we want to find its velocity and acceleration, and in those calculations we are going to need derivatives of these two vectors with respect to theta. Note that unlike our previous fixed unit vectors, these are no longer fixed. As p moves around, they are going to change. So we need to find out how they change. Okay, so first of all we are going to differentiate r hat with respect to theta, and carrying out that differentiation we note that although r hat and theta hat are changing as p moves around, but I hat and j hat are fixed. So we just have to differentiate these coefficient functions. Differentiating cos theta with respect to theta, you get minus sin theta. I hat plus derivative of sin theta is cos theta times j hat. So you see that you have got a very nice thing. This is nothing but theta hat. So the derivative of r hat with respect to theta is theta hat. And when you differentiate theta hat with respect to theta, what are you going to get? You carry out a similar calculation. Differentiating minus sin theta with respect to theta, you get minus cos theta. The minus sign remains, because sin theta when you differentiate gets you only cos theta times I hat, plus this time when you differentiate cos theta you get minus sin theta. So minus sin theta j hat, and you go back to what r hat is. This is nothing but minus r hat. So how nice this is. The derivative of r hat is theta hat, and the derivative of theta hat is minus r hat. So in this respect, r hat and theta hat are just like sine and cosine. When you differentiate sine, you get cosine. When you differentiate cosine, you get minus sine. Something like that. So now we set P in motion. P moves around in the plane, and before we can find the velocity, we have to find the position vector of p relative to this point O, say. Relative to what point, actually, that's up to you, but in this case, say that point is O. O is our origin. Then the position vector of p relative to O is this vector OP. In fact, it is that vector that we saw in that calculation, which is what? What is the magnitude of OP? That is equal to R, and the direction of OP is in the direction of this unit vector R hat. So if we call this position vector vector R, then that is nothing but R times R hat. Now to find velocity of p from this, we have to differentiate this, but not with respect to theta, okay. By definition, that is derivative with respect to time. Okay, so we considered the velocity vector, which is dr dt. That means ddt of this R times R hat. And then we have to use the product rule, by which this derivative equals dr dt times R hat plus R times dr hat dt. Okay, then we simplify notation a little bit. In place of dr dt, we just write R dot. This is a very convenient notation. When you are writing a derivative where the independent variable is time, we use a dot. If it's a second derivative with respect to time, we use two dots. Alright, so we essentially don't do anything with the first term. We just write it somewhat more nicely. But what about this derivative? Note that as the particle p moves around, theta changes. So theta is a function of time, and R hat is a function of theta. So here you are looking at a composite function actually. R hat ultimately is a function of time, but via theta. R hat is a function of theta and theta is a function of time. So you can apply the chain rule here, and by that chain rule, this derivative equals dr hat d theta times d theta dt. So the first term remains like this, and by that same notation, when you apply it to this derivative, it becomes theta dot. So R theta dot times, now you know what this derivative is. This is just your theta hat. So that's how you have obtained velocity in polar coordinates, where there is a radial component in this direction and a transverse component in this direction. The velocity is a sum of those two components, and the radial component is, its amount is this R dot, and the transverse component has this, it is this much, R times theta dot. Next comes acceleration, which is dv dt. Because this is your v, so you differentiate this with respect to t. So that's how you get d dt of this R dot times R hat plus d dt of this product, R theta dot times theta hat. Okay, so this is going to be a little big. So first we carry out this differentiation using the usual product rule. And you note that when you differentiate R dot, you have to use another dot because this is time derivative. So we have R double dot. In that term, R hat is untouched, but then we keep this as it is, that is R dot, and differentiate R hat with respect to t. So these two terms equal the first derivative. But then what about this? We have actually skipped steps here, or rather the author has skipped steps. This is how it appears in the book. So first you differentiate this product keeping this untouched, and there itself there is another application of the product rule. So by the product rule, this derivative means the derivative of this part with respect to t becomes R dot theta dot plus R times theta double dot. Outside you have theta hat, and then in the next term you keep this intact and you differentiate theta hat with respect to t. So then in the next line we replace this derivative and this derivative by this and this respectively by the chain rule. and the others remain as they are. So this part remains the same. In this part, we have written dr hat d theta times d theta dt plus this also stays the same plus r theta dot times d theta hat d theta times d theta dt. Okay, and then we see, let's see what we get. So this is r double dot r hat plus, what is this? This part can be written as theta dot in our simpler notation. So it becomes r dot theta dot times, what is this? Again, we know this, and that is why we replaced these derivatives, because we know these things. We know derivatives of those polar unit vectors with respect to theta. This is theta hat plus, and then this part remains the same, r dot theta dot plus r times theta double dot, and outside you have theta hat plus, what is this? You have one theta dot here, another theta dot you are getting from here. So r times theta dot square, and what is this? D theta hat d theta minus r hat. You remember that previous calculation. So now we gather things, gather like terms. You look at those terms which have r hat with them, this one and this one. So from them, if you take r hat common out, you are going to get r double dot minus, there is a minus sign, okay, don't forget that, minus r times theta dot square, outside you have r hat plus this term has theta hat and this one also has theta hat. So you combine them and you are going to get r theta double dot plus r dot theta dot, and there you have another r dot theta dot plus 2 r dot theta dot, outside you have theta hat. So this is your acceleration vector. This is the radial component and this is the transverse component. The total acceleration is a linear combination of these two vectors, a sum of two vectors, one along this line, the other one along this line. It looks pretty complicated, but that's how things are. You might genuinely ask why we need these polar representations of velocity and acceleration, because they really look very complicated. The answer is that they will be useful in studying motions where there is a rotational aspect, where things are not really along a straight line. There these things will be useful. Let's see one example next, example 2.6. A particle sliding along a radial groove in a rotating turntable has the following polar coordinates, which are functions of time given by this. R is Ct and theta is omega t, where c and omega are positive constants. So there is a turntable and there is a groove, radial groove, which goes out means it's along a radius of that circular turntable, and there is a particle in that groove. So as the turntable rotates about its center, the particle moves along the groove outward, and in doing so, at the same time it's rotating also like this. And at any time instant t, these are the polar coordinates of the particle with respect to some initial line and some pole which are there in the background. We have to find the velocity, speed and acceleration of the particle at time t, and there is something else also in this example which I did not feel like writing. We have to also show that the velocity and acceleration vector, the angle between them is an acute angle. Solution, so you straight away write what velocity is in polar form, r dot r hat plus r theta dot theta hat. So because your r is Ct, so differentiating with respect to t, you get c. So the first term is c times r hat, and you just write what r is here, Ct, and what is your theta, omega t. So theta dot will be omega. times theta hat, because you have a common term c, you can take it outside. So this is your velocity. Now the magnitude of velocity will be speed, but how do you find the magnitude? You might get confused here suddenly. You just apply the first property of scalar products of vectors here. By that property, the square of the magnitude of v equals v dot v, which equals c square times this dot this. I ran out of space here, so I wrote on that side. And then you use the distributive laws and the other laws of vectors that you have encountered so far. Or to put it more simply, you just multiply. R hat dot R hat, do not forget that the product is dot product. Okay, whenever you have two vectors in this multiplication, the product is dot product or scalar product, plus R hat times omega t theta hat, means omega t will come outside. Outside means you can write it outside by one of the properties again. You go back and see, this is something we have already seen, times R hat dot theta hat. Similarly, then you multiply these two by this. So the next term becomes omega t times theta hat dot R hat plus omega t times omega t is omega square t square theta hat dot theta hat. Now just like I and j are perpendicular unit vectors, R hat and theta hat are also perpendicular unit vectors. So this dot product is 1. This one is also 1. So that's how you are getting omega square t square. But these are 0 because R hat and theta hat are perpendicular. And then you take positive square root on both sides. So that's how you get the magnitude of v, which is your speed. C times the square root of 1 plus omega square t square. Okay, so next of course we have acceleration. You recall that acceleration is r double dot minus r theta dot square times r hat plus r theta double dot plus 2 r dot theta hat. Don't worry about memorizing these things, okay? The more you use them to solve problems, automatically they will just simply be with you. But anyway, if you don't remember, you can just see in your book. Now also, what is r? R is ct, where c is a constant, and theta also is omega t, where omega is constant. So the second derivatives of these quantities with respect to t are 0. And what is theta dot? Theta dot is omega. So here you have, I have put what r is ct times omega square, r hat. This term is 0, and here r dot is c and omega dot, theta dot is omega. And then you can take c omega common out. So this is your acceleration. So that's the example. And let me just end the video here itself. In the next video on mechanics, that means next week, we are going to see general circular motion. So far we have seen uniform circular motion, where the motion is along a circle and the speed is also constant, but now the speed is not necessarily constant. For example, you can think of a pendulum where the bob is swinging back and forth like this. That motion is not happening at constant speed, of course, because as the bob comes down at the bottom of the motion means just when the string of the pendulum is vertical, at that instant the speed is maximum. The more the bob goes towards that side or this side, it slows down and eventually it stops, and then again it continues in the other direction. So we are going to see those things.